man. It's been a while, man. Gleeful. Man, welcome back, man. Modest I Reacts. It's been about 2 months. Been about 2 months, man. First I'd like to say, if y'all want me to use the fisheye lens, let me know. This is the regular lens, but I got this really goes to your phone. It's like camera lenses for your phone, but I could use this over the MacBook camera. So, give another perspective on videos, you know. What up, Modest Gang, man? I'm back, man. It's been a while. I've been sick a lot and just been working, man. I've been working like 6 days a week, so only days off I have is a Sunday. So yeah, I ain't wanna. That was too much. But hey, man, welcome back to ISS. I'm the teacher of ISS. You know what I'm saying? And we got the principal here today in class. We'll say what's up to the principal. So you know what I'm saying? We just, what I'm saying? Just we gotta switch it up a little bit. We're gonna learn about some math today. Math, one of my favorite subjects. But with the easy stuff. Once you got past the hardest math class I took, I think I was in when I was in college, I took probability and stats. That wasn't math. I don't know what that was. That wasn't math. But C is passing. Let me hold on, cause
It's a math competition for undergraduate students. It's a 6-hour-long.
I hope that ain't loud, cause it's loud in my headphones, but it don't be loud on the video.
So the highest possible score would be 120. And yet, despite the fact that the only students
Hopefully that's good.
here are those who clearly are already pretty interested in math, the median score tends to be around 1 or 2. So it's a hard test. And on each one of those sections of 6 questions, the problems tend to get harder as you go from 1 to 6. Although, of course, difficulty is in the eye of the beholder. But the thing about those 5s and 6s is that even though they're positioned,
I never even heard of this.
problems on a famously hard test,
Yo?
these are the ones with the most elegant solutions
Okay.
available. Some
Okay.
that transforms it from very challenging to doable. Here, I'm going to share with you one problem that came up as the 6th question on one of these tests a while back.
Alright.
Rather than just
Hey, man, if y'all can figure this out, man,
surprisingly short,
let me know.
take the time to walk you through how you might have stumbled across
Yeah, I ain't never get to calculus.
that is, make a video more about the problem solving.
No, sir.
About the problem.
No, sir.
So anyway, here's the question. If you choose 4 random points on a sphere and consider the tetrahedron with these points as its vertices, what is the probability that the center of the sphere is inside that tetrahedron? Take a moment and kind of digest this question.
Time out, man. What? Well, hold on. Let's go back.
The tetrahedron with these points as its then about the problem.
Hold on. I don't even know what he just said. What did he just say?
If you choose 4 random points on a sphere,
Okay.
and consider the tetrahedron with these points as its vertices, what is the probability that the center of the sphere is inside that tetrahedron?
Man, hell no, man. What are we talking about?
You might start thinking about which of these tetrahedra contain the sphere center, which ones don't, how you might systematically distinguish the two. And how do you even approach a problem like this?
Yeah,
Where do you
man.
even start? Well, it's usually a good idea to think about simpler cases, so let's knock things down to 2 dimensions, where you'll choose 3 random points on a circle, and it's always helpful to name things, so let's call these guys P1, P2, and P3.
Okay.
What's the probability that the triangle formed by these points contains the center of the circle? It's really easy to visualize now, but it's still a hard question. So again, you ask, is there a way to simplify what's going on?
Okay.
Get yourself to some kind of foothold.
Alright.
Maybe you imagine fixing P1 and P2 in place, and only letting that third point vary. And when you do this, and you play around with it in your mind, you might notice that there's a special region, a certain arc, where when P3 is in that arc, the triangle contains the center, otherwise not. Specifically, if you draw lines from P1 and P2 through the center, these lines divide up the circle into 4 different arcs. And if P3 happens to be in the one on the opposite side as P1 and P2, the triangle has the center. If it's in any of the other arcs, though, no luck.
Okay. I get it.
Here that all of the points of the circle are equally likely. So what is the probability that P3 lands in that arc? It's the length of that arc divided by the full circumference of the circle, the proportion of the circle that this arc makes up. So what is that proportion? Obviously that depends on where you put the first 2 points. If they're 90 degrees apart from each other, then the relevant arc is 1/4 of the circle. But if those 2 points are far apart, that proportion would be something closer to a half.
Who's blowing up my phone on Facebook? Goodness.
So think about this for a moment. P1 and P2 are chosen randomly, with every point on the circle being equally likely. So what is the average size of this relevant arc?
50?
Maybe you imagine fixing P1 in place and just considering all the places that P2 might be. All of the possible angles between these 2 lines, every angle from 0 degrees up to 180 degrees, is equally likely. So every proportion between 0 and 0.5 is
50. Come on, man.
The average proportion is 0.25. So, if the average size of this arc is 1/4 of the full circle, the average probability that the third point lands in it is 1/4. And that means that the overall probability that our triangle contains the center is 1/4. But can we extend this into the 3-dimensional case? If you imagine 3 out of those 4 points just being fixed in place, which points of the sphere can the 4th one be on so that the tetrahedron that they form contain the center of the sphere?
Man, I would have got this question wrong.
Draw some lines from each of those fixed 3 points through the center of the sphere. And here it's also helpful if we draw some planes that are determined by any pair of these lines. Now what these planes do, you might notice, is divide the sphere into 8 different sections, each of which is a sort of spherical triangle. And our tetrahedron is only going to contain the center of the sphere if the 4th point is in the spherical triangle on the opposite side as the first 3. Now, unlike the 2D case, it's pretty difficult to think about the average size of this section as we let the initial 3 points vary. Those of you with some multivariable calculus under your belt might think, let's just try a surface integral. And by all means, pull out some paper and give it a try.
Nah.
And of course it should be.
Nah.
This is the 6th problem on a Putnam. What do you expect? And what do you even do with that? Well, one thing you can do is back up to the 2-dimensional case and contemplate if there is a different way to think about the same answer that we got. That answer, 1/4, looks suspiciously clean, and it raises the question of what that 4 represents. One of the main reasons I wanted to make a video about this particular problem is that what's about to happen carries with it a broader lesson for mathematical problem solving.
So,
What about those 2 lines that we drew for P1 and P2?
alright, so far, do y'all understand what's going on? Okay. Show of hands. Show of hands, man. Just show your hands, y'all. Alright. You know. Hey, man, wake up back there, man. So everybody blowing up my phone right now. What is going on? I'm gonna continue the video.
They made the problem a lot easier to think about. And in general, whenever you've added something to the problem setup that makes it conceptually easier, see if you can reframe the entire question in terms of those things that you just added. In this case, rather than thinking about choosing 3 points randomly, start by saying choose 2 random lines that pass through the circle's center. For each line, there's 2 possible points that it can correspond to. So just flip a coin for each one to choose which of the endpoints is going to be P1. Likewise for the other, which endpoint is going to be P2. Choosing a random line and flipping a coin like this is the same thing as choosing a random point on the circle. It just feels a little bit convoluted at first. But the reason for thinking about the random process this way is that things are actually about to become easier. We'll still think about that 3rd point, P3, as just being a random point on the circle. But imagine that it was chosen before you do the two coin flips. Because you see, once the two lines and that third point are set in stone, there's only four possibilities for where P1 and P2 might end up, based on those coin flips, each one being equally likely. But one and only one of those four outcomes leaves P1 and P2 on the opposite side of the circle as P, with the triangle that they form containing the center. So no matter where those two lines end up and where that P3 ends up, it's always a 1/4 chance that the coin flips leave us with a triangle containing the center. Now that's very subtle. Just by reframing how we think about the random process for choosing points, the answer 1/4 popped out in a very different way from how it did before. And importantly, this style of argument generalizes seamlessly up into 3 dimensions. Again, instead of starting off by picking 4 random points, imagine choosing 3 random lines through the center of the sphere, and then some random point for P4. That first line passes through the sphere at 2 points, so flip a coin to decide which of those 2 points is going to be P1. Likewise, for each of the other lines, flip a coin to decide where P2 and P3 end up. Now there's 8 equally likely outcomes of those coin flips, but one and only one of them is going to place P1, P2, and P3 on the opposite side of the center as P4. So one and only one of these 8 equally likely outcomes gives us a tetrahedron that contains the center. Again, it's kind of subtle how that pops out to us, but isn't that elegant? This is a valid solution to the problem, but admittedly, the way that I've stated it so far rests on some visual intuition. If you're curious about how you might write it up in a way that doesn't rely on visual intuition, I've left a link in the description to one such write-up in the language of linear algebra, if you're curious. And this is pretty common in math, where having the key insight and understanding is one thing, but having the relevant background to articulate that understanding more formally is almost a separate muscle entirely, one that undergraduate math students kind of spend most of their time building up. But the main takeaway here is not the solution itself, but how you might find that key insight if it was put in front of you and you were just left to solve it. Namely, just keep asking simpler versions of the question until you can get some kind of foothold. And then when you do, if there's any kind of added construct that proves to be useful, see if you can reframe the whole question around that new construct. To close things off here, I've got another probability puzzle, one that comes from this video sponsor, Brilliant.org. Suppose that you have 8 students sitting in a circle taking the Putnam. It's a hard test, so each student tries to cheat off of his neighbor, choosing randomly which neighbor to cheat from. Now, circle all of the students that don't have somebody cheating off of their test. What is the expected number of such circled students? It's an interesting question, right? Brilliant.org is a site where you can...
Alright, yeah, he plugging his little sponsor. Yeah, that was interesting. I actually took like a kind of like an algebra math test in like middle school, I believe. Might have been high or elementary. I think it was either elementary or middle school. I took like a because my grades were so high in math that the school like submitted my name to some math test or something like that, and then I passed it. Honestly, I passed it, and I was able to allow me to skip grades. Honestly, I could have skipped like 2 grades, but my mom didn't want me to. Hey man, it is what it is. You know, I would have skipped to 6th grade. I would have went right from 5th to 7th. I would have went from 5th grade to 7th just because I passed that math test the school put me in. So, you know, it all worked out, man. Hey man, when I upload, I appreciate the views, man, because you don't gotta watch me, you don't gotta like me, but if you ride with me, I'm riding for life. Modest gang out, man. Stay gleeful.